Hello, everybody. Thank you so much for joining our session today. I'm very excited to be presenting Dr. Gareth Conduit, who will be giving an overview talk about how machine learning is being applied to the field of energy storage. More specifically, he'll be speaking about some of the ways it's being applied for battery modeling, particularly to accurately determine state of charge and state of health and remaining useful life of batteries. A large part of the development of electric vehicles depends on knowing cycling performance and cost and safety of batteries. And currently, this can be a challenge due to the trade-off between accuracy of predictions and of the state of batteries with the computational complexity in determining them. Dr. Gareth Conduit holds a PhD in condensed matter physics at the University of Cambridge, and he's currently a Royal Society University Research Fellow at the Theory of Condensed Matter group at the University of Cambridge. And he's also a Chief Technology Officer at an AI company called Intelligence. And his research really revolves around developing and applying machine learning to designing new materials and drugs. And through his company, Intelligence, he has these machine learning tools available to transform client sparse experimental data into these meaningful predictions. And so his award-winning work is applied to a really wide range of industries, such as healthcare, drug discovery, and automotive, just to name a few of them. My name is Sajeda, and I am the machine learning and physics stream owner at AISC. And without further ado, I will give the floor to Gareth to begin the presentation.
Well, thank you, Sajeda, for such a kind invitation, or kind introduction, and the invitation to share with you today some of the work that we have been doing, both at the university and also at Intelligence, on developing novel machine learning methods, and in particular applying them to develop the next generation of batteries. Now, we have developed our Alchemite machine learning tool, which has been spun out of my academic group at the University of Cambridge and is now being commercialized and taken to market by Intelligence. The Alchemite machine learning tool has a specialist capability that it is able to extract information from the typical experimental data sets that we would find in the sciences. And those are data sets that are particularly sparse and noisy. So by sparse, we mean not everything has been measured about every battery, either because the people who did the particular measurements were not interested in that particular property, or due to cost. But nevertheless, our novel machine learning tool is able to handle such sparse data sets. And this in particular allows us to take in many different sources of information, that we can combine a large number of cheap to perform computer simulation, combine that with analytical physical laws of nature, and merge that with the much more rarefied experimental data. And thus we are able to get the best of all worlds to make the very highest quality possible predictions. This in turn, with a better machine learning model, allows us to make better predictions and reduce the need to perform additional expensive and timely experiments. And that in turn allows us to discover new materials, discover new drugs, improve batteries more rapidly. Now, the methodology that I'm presenting is completely generic. It's really a bit of maths that applies to sparse data. And this means that we have been able to already successfully apply to a wide range of problems, be it in materials discovery, be it in batteries, or also we do a lot of work in the pharmaceutical sector. But today I'm going to exemplify what we do through a discussion of batteries, and in particular we were going to really be describing a project we did with Samsung Electronics on designing new parts of batteries, new cathodes, and these are materials on one side of the battery that contain often nickel, cobalt, and manganese elements. Now, we should first think about what do we want to achieve from our batteries, which we've already heard in the kind introduction, a couple of things. That at the top, I've got here an electric car, though batteries can also be found in your phone and many other things. But one thing that we definitely want out of the battery is that it can be used time and time and time again. We all know that with our phones, with our laptops, computers, that after a couple of years that the performance of the battery degrades, that lifetime reduces. And we want to really be able to maximize the number of cycles that we can pass the battery through, represented up the top here by the car being repeated several times. So that's going to be a very long time scale property we need. But we also need a shorter time scale property, which is the performance over one single charge-discharge cycle of our battery. That we need the battery to hold as much energy as possible to give our car, our phone, as much range as possible. And that range anxiety is something that's really holding back the application of batteries in electric vehicles at the moment. And it's also important what the maximum amount of power at a certain instant that the battery can deliver for us. That could equate to the speed of our car. Now, we also need to remember that as well as all these properties, that we're always working in a commercial sector, and therefore that the cost of the battery is always going to be important. We need to really keep a lid on that to really minimize it. So I've got here listed some of the practical properties that we need from the battery that the end customer, the end client, would be interested in. But we can now attempt to translate those into properties of the battery the scientist would be interested in. Rather than the number of uses, we can talk about the number of charge-discharge cycles the battery can go through. And rather than the range of the battery, we can talk about the total amount of electrical charge we can get on that battery. And rather than the power delivery of the battery, we can talk about the electric potential, almost the voltage of the battery. And down the bottom, I think it's a rather universal property for humans, is the cost, just translates straight to the cost of the battery. And that will comprise of both the cost of the materials we put in the battery, but also into the manufacturing cost, how difficult it is to put the battery together. So these are all some of the properties of the battery we are going to be interested in. There are other ones as well we will touch upon later. And to make a successful battery for real life, it is essential that we get all of these properties of the batteries to all work at the same time. Now, to understand such a multi-parameter problem, we've opted to turn to machine learning, which is just this black box that I've got at the center. And it's just a tool that's going to take in perhaps the composition of the battery. So here, in a very physics point of view, we've got all the different elements that we put into the battery, and also the clock and the thermometer, the processing variables, the how do we make the battery. And we just need that mathematical black box at the center that we put that properties in, and it spits out for us all of those physical properties that we need to get correct. Now, for the machine learning, perhaps one option is to use a neural network, a mathematical representation of how possibly the brain works. But one thing it definitely has in common with the human brain is it needs to go to school, to university, to learn about batteries. So therefore, we take a database of pre-existing battery properties. So I've got those represented over there on the right, and we push those in to the machine learning tool so it can learn about batteries. And then once it has learned, we can flick this arrow back around and present to the tool a composition that it's never seen before, and it will make for us predictions of the properties of the battery. And then ultimately, we will cycle through millions and billions of possible material compositions to hit upon the one that gives all of the correct properties that fulfill the targets laid out by the scientists, by the engineers, by the customer. So that is what we're trying to achieve in machine learning, but we're going to come up against a bit of a hitch, and that is that we don't have very much data for some of these crucial properties. And this is often because the experiments are really expensive to do, maybe $100,000 a pop, And so we don't have very much historical data, and it's going to be expensive to gather more. And that's going to be the regime that we are trying to develop our machine learning to work well in, is a regime in which we have extremely little experimental data to train off, often fewer experimental data points than there are input parameters that we need to define on the left. And so it sounds almost mathematically impossible to solve, but we're going to see later how we can attempt to do that. And the major trick that we're going to do is to rely on the correlations between different properties, and here is going to be the correlations between experimental methodologies on the left and the other computational modeling methods, such as where you put all the physics equations in and try to solve them, on the right. So over on the left, we've got the experiments, and these are good because the experiments are usually or often extremely accurate. And next down in green, they also tell us the actual quantities that we need to know about the battery, such as the number of charge-discharge cycles. But the disadvantage of experiments I've already outlined is we don't have very many results for them, typically because they're expensive to do and they take a long time to do. But over on the other side, underneath me, I'll just get myself out of the way, then we have computational methodologies. Now, these are typically solving some first principles computer physics formulae for the system, which usually has a lot of approximations behind them. They are usually less accurate than experiments, and they also don't typically calculate the actual properties of the battery we are interested in, but some other proxy quantity. So that's both weaknesses of computer simulations, but advantages is that we can perform, they're quick to do, we can perform them on demand on the current battery compositions we're interested in right now, and they're also going to be cheap to perform, and so we can do a lot of them. And what we're going to try to do in our machine learning is to get the best of both worlds. Can we use machine learning to not just predict properties of batteries, but to effectively juxtapose these two methodologies so we get the green parts of them both, the accuracy of experiments and the focus on properties we're interested in, but combine that with the computer simulation's ability to be performed on demand and to be very cheap to do, to get the greenness but not those red disadvantages. So that's what we've been trying to set up in our machine learning methodology. Now, to try to give you a little bit of an idea under the hood of how this works, I've just got on the left here a graph of an experimental quantity, could be number of charge-discharge cycles as a function of the composition of the battery, perhaps the amount of nickel atoms that we put in. Now we've got 3 experimental data points shown there in blue, and then in light blue is our machine learning model for that property, where I've also shown we also always predict the uncertainty in our machine learning model. And we can see near to where we have experimental data points, the model's not too bad, but on the right-hand side of the graph where we're now extrapolating, there is a lot of uncertainty in our predictions, which is going to really hinder the ability to use this to actually design new batteries. But we also have access to complementary first principles computer simulations, which are shown the right on red. Now, these may not be exactly the same property, they might not be 100% accurate, but they should provide a good guide. And because they're cheap to do, we get lots of results for them, and so we can readily build an accurate machine learning model over them. Now, what our methodology is going to be capable of doing is not just training these 2 separate machine learning models, but is going to plot, is self-identify and then internally plot this graph that I've shown in the middle of the 2 y-axes against each other. So it's going to notice that if it were to plot a graph of the experimental results versus the simulation results, where it has access to them, they lie almost on a straight line. Now, of course, we don't have very many experimental data points, so we don't. But fortunately, because they lie almost on a straight line, we don't need very many data points to define this line. The 3 that we have is at least enough to identify that they lie on a straight line. And of course, the line may not be perfectly straight because the simulations don't map perfectly onto experiment. They're approximations, and so there might be a shift in the line. Perhaps it's not at 45 degrees, but if the simulations are good, hopefully it will be close to a straight line. And this then allows us to do a trick to get much better predictions for the experimental quantity. And mechanistically, what will happen is that if you see my mouse, firstly, we'll give it a new composition over here on the right, that we'll see that we get an inaccurate prediction for experiment, and the tool go, uh-oh, this is not going to work. We can't do this very difficult extrapolation, but instead it will go over here and go, I can go and predict what the computer simulation result would have been. Over here, of course, we want to do machine learning rather than a fresh computer simulation because the simulation might still take an hour or so, but the machine learning should take a microsecond. But it will go, I've got loads of data here to understand this exact landscape. I can make a very accurate prediction. So we've done one accurate interpolation. Then it would go over here and say, I'll take my simulation result and I can turn that into an experimental result. And this is a very simple graph. I didn't need very much data to define it. So that's a second easy interpolation. And then it'll put that result down here as the new blue result down here, which is much more accurate. And so in effect, rather than over here, we're doing one extremely difficult, it might be mathematically impossible extrapolation. We are instead doing it by 2 stacked interpolations, one here and then one here. And this is how we're going to be able to get away with having so few experimental data points by instead using this proxy quantity in the difficult landscape. As that's the idea behind our methodology. In reality, it's a bit more complicated, that we have to self-identify all of this. As often, we don't know the physical laws, and we might be merging multiple properties together all simultaneously rather than just one, but this is the method in a nutshell. So once we've got that, we're then well positioned to be able to make predictions for this difficult experimental quantity. We've got our machine learning model. We can design the new batteries. As this is kind of a map about how the information is going to flow through the system, that we'll start off over here on the left with the composition of the material and knowledge of where the atoms are. And then some of the data will flow through down here to the second machine learning model, but most will firstly will go up here where we fed in knowledge of first principle simulations into this machine learning model to make predictions for properties such as the ground state of where the atoms physically sit in the lattice, the voltage of the lattice. We can predict the size of the material, the volume of it, and also this property here, how far the lithium ions move as the battery is used. And then we're going to use these physical properties as an input and merge it with the few experimental data points we have to predict the actual physical properties we're interested in. And we can see, for example, here that knowledge of the lithium migrations, that's where the atoms move about in the crystal, is going to tell us how that crystal structure is disrupted, and in turn, how many charge-discharge cycles we can push the battery through and how quickly we can charge the battery up and how quickly the battery can give us energy back. Whereas the knowledge of the volume of the battery here from the simulations is going to tell us how much the volume changes. And this is important because these batteries actually get bigger and smaller as you discharge them. And also the density, which is really important for transport applications. That's how heavy the battery is going to be. So we can see how effectively that's all done automatically under the hood, how we can use knowledge from those computer simulations to help really guide the extrapolation of our few experimental data points. Now we went on and actually applied with this with Samsung, where the chief goal was to improve the number of charge-discharge cycles we can push the battery through, which really means that we want to reduce the migration of lithium ions, which means that we've got a picture of the crystal structure where all the atoms sit in the battery here, and the different color circles correspond to different atoms, with the lithium shown by the cyan. And we want it so that as we're pulling lithiums in and out as we're using the battery, that the crystal structure is robust. And the structure over on the left, the original one that they were previously using, is not so robust. In fact, it only goes back to what it used to be 82% of the time. Whereas the other structure on the right, the proposed one our machine learning identified, is much more robust. As we pull those lithium ions in and out, as we're charging and discharging the battery, the atoms go back to where they started from, and so it is 100% robust, which means you should be able to, the battery won't get damaged. We can use it over many more charge-discharge cycles. So that's just one property. In fact, there are several others that we had to get right, such as the voltage of the battery, the amount of charge the battery can store, the density of the battery to make sure it's lightweight, and of course the cost. And our machine learning model ensured that we were preserving all of those properties whilst at the same time optimizing this lithium migration to give the battery a longer life. And so this project was a poster child within Samsung to show the opportunity of machine learning. They then went off and started experimentally making these batteries and looking at them, though unfortunately I cannot share with you those results. But it also served as a real example about how we can use machine learning in the future in this kind of battery project and in material design, that it really showed how it allows us to very rapidly design new batteries. The design of the project took a year. Each battery could be designed in a few hours or so, which is much quicker than the typically 10 years or so that the typical material design project would take. And it also enables a new business model where at the moment when Samsung is designing the next phone, designing a new electric car, then because the batteries take so long to themselves design, they just have to use a battery off the shelf, the one that has the best approximate properties for the application. And in turn, when they're designing new batteries, they have to think, oh, in 10 years' time, I might want my battery to have this performance, and so we'll start to design those now in the hope that actually you've made a good guess and that in 10 years' time, that is actually the property you want. But now, because we can design these batteries so much more rapidly, it allows a bespoke battery to be designed at the same time as the new phone, at the new car, to really bring materials into the heart of the design process. So we had a lot of fun on that project, and it certainly laid the path for other projects that we have done. Now, another area that we've been working on in batteries, which is less to do with the materials, is to try to understand the properties of a battery once they have been made. Now, this has actually led to the writing of this Nature Review article, which led to my invitation here. So I just highlight a few examples from it, and in particular, how our methodology of using machine learning to merge together different properties, to merge sparse data with a more complete but cheap data set is proving to be very effective. And each of these three examples I highlight in blue within the text in that paragraph that is shown, the two sources of data. Now, the first is, can we develop a machine learning tool that we can embed as a battery management system actually physically on the battery as it is shipped, so that the battery management system can learn how the battery is being used in real life, how it is evolving, and thus make future predictions about how this battery is going to last, what its remaining useful life would be, or to recommend to the device how the battery could be used differently in order to prolong its life. So, of course, that if you just learn from that particular battery, you haven't got very much to go on, but we can supplement it with other data from batteries that have already been used, that are being tested in the factory. So we've got two sources of data, historical data and how this particular battery is performing. And it's already been trying to develop battery management systems with those two separately, but we're now well positioned to be able to merge those together with machine learning to allow us to make really bespoke predictions for how a particular battery will perform, but educated from the information from all historical use cases of other batteries. Now, the next one in the list is the very different timescales that batteries are being, and we need to understand the properties of batteries over. We have very short timescales, that is just in a particular charge-discharge cycle, how many more miles can I drive my car, how many more hours will my phone battery last. But we're also interested in the longer term. How many more charge-discharge cycles can I put my car through before the battery's worn out and I need to take it for a service? And our type form of machine learning model is very effective at merging together data from those two very different timescales and start to use one of them to help inform the other. Now, the third idea is something that we've been working on with a couple of real-life customers. These are battery manufacturers who are interested, or who, once they make a battery in the factory, they put it through a small number of charge-discharge cycles, firstly as part of quality control, and also to understand how that particular battery will perform. And then they can ship batteries that will perform in different ways to different customers. So, for example, some applications, you need the battery to be able to deliver a very high current, a very high amount of power in a short time, like a car starter motor, in which case they need batteries that are good at that. Whereas just off the same production line, you might get different batteries that aren't quite as good at that, but have a longer number of charge-discharge cycles they would be able to go through before wearing out. So they could be sent instead to a different customer that's interested in that property. But in taking data from the first few cycles and extrapolating it out is going to be a very difficult problem for machine learning to do. And this is where we can again merge together data sets. We can merge together the data set from this particular battery, its first few cycles, and merge it together with other data sets we have of the batteries that the factory has tested over the long term, or data from some other batteries that are already out in the field and are in service. And so we can use that experience, but merge it together with a very bespoke data for a particular battery to make higher quality predictions. So that's just 3 ways in which we can use such a machine learning methodology, and you can read much more about them in that paper. Now, that's everything about batteries, but just to say that our methodology is very generic and it's been already applied to a wide range of other material design problems, such as up at the top, we've been working with GKN, who are first-tier aerospace manufacturer, on designing new alloys for 3D printing, with Rolls-Royce, the engine manufacturers, on new alloys for use within their engines. In fact, you can see pictures there of the actual alloys that we proposed that were experimentally made and then tested, and that was done sufficiently long ago and they've been patented. That down the bottom, actually, a handful of those papers are about those alloys. I've been working with BP on the design of lubricants. We've also done an awful lot of work with some drug companies here on designing new small molecule drugs. And a lot of these projects have led on to proposed materials that have been experimentally verified. And in fact, some of those have been written up in those papers there. And so we're very proud that we've got actual real life validation of our methodology. So, to summarize, I've described today a different form of machine learning that we have been working on, which we call Alchemite, which is really set up to handle sparse data sets and is able to merge together many different streams of information. And I've focused here today really on merging first principles computer simulations together with experimental data. And this allows us to extract more knowledge than other methodologies to make higher quality predictions. I described how we did some work to design new cathode materials for batteries, aiming at a longer lifetime for the batteries whilst maintaining other properties, and also how we could use that same methodology as part of battery management software. So if you want to know any more, I've got some links down the bottom there, including an online demo you can go and play with to optimize materials and some papers. And with that, I'd like to again thank the organisers for inviting me along today. Thank you for listening. And I'll now be very happy to take your questions. So thank you.
Thank you very much, Dr. Gareth Conduit. That was a very interesting presentation. We're going to start with the discussion now. So I have a few discussion questions I've prepared myself. And if there are any questions from the audience, they can just type it in the chat and I will relay them to you. So first of all, I would like to hear about what kind of real issues you might have when implementing these models for data from a customer.
So I think that's a very good question. So there's a whole stream of issues. The first is that the customers typically don't have their data beautifully organized in a proper database or a spreadsheet. That it's typically historical data that different members of their team has taken at different times and is in dust. If we're lucky, it's in some dusty filing cabinet in the corner of the office, and if we're unlucky, it's spread between several filing cabinets or is lost. And so the first thing we often have to work with our customers on is bringing their data together, and we often have to supplement it with data that you can freely get online. So then after we got the data and are able to make models, and then there's going to be hiccups along the way if some of the data is not of the highest quality, or we might have to think of a proxy physical quantity to help provide the additional data to guide extrapolation. The next thing down the line, which is often in a way surprising, is that often the customers are not exactly sure about what material properties, target physical properties they actually want. See, they say, oh, we want to make a better material, but then you say, well, how many charge-discharge cycles do you want the battery to go through? And they just do not know. And so really trying to pin them down on what they actually want to achieve is a second important step. It's something they often didn't used to have to worry about. But once we got that completed, then often the rest of the project is great fun to work with them, and it's really great when they go off and make the materials and they actually work in real life.
That's very cool. Thank you so much. So just to kind of ask something else. So I was wondering, in your work, what do you think is the most useful data? Would you say experimental data is more useful or computational?
So as we have a real focus on dealing with the real life in our company and selling to customers, it would almost always be the experimental data that is the most valuable to have, because it's correct and is of the properties often of interest to the customer. Now, that being said, all things being equal, the computational data can deliver some very complementary and important insights that often these first principles computer simulations can be done at an atomic length scale, and for some physical properties that depend on atomic length scale, such as that charge discharge of the battery and watching those lithium ions go in and out, then there the computer simulations are in their own right essential and are telling you something you cannot get from experiment. Mm-hmm. And then the other real important usage of the computational data, the real advantage of it, is that it's easier to do and it's cheaper and much more timely. So in that way, it's absolutely essential that we have access to the computer simulations, because the experiments are just far too expensive to do. Often they're about $100,000 a go, and they take 6 months to perform a single one of them. Whereas the computer simulations we can do at the drop of a hat. And so using those computer simulations to help really guide the extrapolation of those very expensive experiments is absolutely essential, and it very dramatically improves the quality of our results.
Yeah, makes sense. I'm also just wondering if you can kind of compare machine learning models to traditional analytical models and, you know, their pros of each. Yeah.
Oh, no, absolutely. So we often also do merge in physical models. Now, we would do that by pretending that it is another computer simulation, but a very cheap one, and we would make millions and billions of results from them, and that's often a way we're doing this. But the analytical models are going to be very important, firstly because they contain some physical understanding that the machine learning by itself cannot pick up upon. And this is particularly important with one customer we're working with, where they want to extrapolate their data a long way. And they know that the approximate physical law is approximately correct. And we're using that extremely heavily to help guide us to extrapolate outward. And the second thing that we often use the physical law for is that the physical law, well, it contains some physical knowledge from some other systems, such as the knowledge of quantum mechanics. We learned it from one system, and we're now transmitting it across to this one. And if we were try to derive that ourselves from the machine learning model, then we're going to come unstuck, because we use a lot of data to derive this already known physical law, when we'd much rather use that data to do something else. And so often what we would do is say for density of a material, that's approximately the mass of all the atoms, the elements you put into it, that we would have an approximate density that just comes from that rule of mixtures, and then we would present to the machine learning model the difference between the analytical and the experiment, just a tiny little correction factor. And we get the machine learning to focus on that bit that we can't write a formula down for. Whereas the gross behavior, we've already pulled out of the analytical laws. And so I think from our point of view, really have to use everything that we can get our hands on to improve the quality of the predictions.
Yeah, that's really cool. I wanted to ask you also some questions about training. So how do you train from missing data? So sparsely labeled data, what kind of, how do you overcome that, and how do you do your training for data that is sparse?
Well, so we are presented with the sparse data, so it would look like often a spreadsheet where it's just got some blank cells, and then we drop that into the machine learning model. So if I go back to the slide where I had, they can see this slide, then the machine learning model is on the left. It's got that blue graph, it's got the sparse data there. So it's going to pick up that there's not very much data present. So it's going to have some large uncertainties on its predictions. And so that is one of the triggers that internally it knows that it's going to need to think twice about this. And that's what's then going to motivate perhaps the plotting of the graph at the top center here, the experiment versus simulation graph, that it's got to automatically identify that there's a very strong correlation here. So despite there being just 3 data points in what might be a more than 3-dimensional parameter space, so it's essentially mathematically impossible to do, that the tool's internally got to do some, what's in effect, Bayesian inference, work out that this type of graph is what it needs to do, and then be ready to exploit that graph when it's presented with the real life situation. And so it's internally, it's got to be able to work out what is sparse, what might be sparse when it's making predictions, and then have it at its disposal a plan B. But then it's also got to have a plan C, because it might be that its plan B relies on some other data that's sometimes there and sometimes not there. And when it's not there, it's then going to find another route through the problem. And ultimately, the more sparse the data is going to be, the larger the uncertainty will be in your predictions. But at least we're honest and we know what the uncertainty is, so you can be steered away from proposing something to a customer that has a large uncertainty, so may well not work in real life. Yeah,
that makes sense. And I kind of wanted to expand on that. So I had read a recent paper for another talk about kind of the same idea for a general lake model. So they had very sparse experimental data, and how they overcame that, like with only the sparse data, is that in their loss function, they had terms that didn't rely on labeled data. So some of the underlying physics equations didn't need a labeled data. So they would train it with that in the error function. and it would help make accurate predictions. So I was wondering if you have done anything similar to that, or if you just do this extrapolation instead.
Yes, we have played around with the loss functions. So that's what you'll typically find if you're doing a neural network type model. So we were playing around with those in a different way, in trying to impose physical laws of nature onto our system. And so, so with a battery, for example, we know that if you take your battery and it's got a positive and negative terminal and you flick it around the other way, then the properties of the battery should be exactly the same. All you do is multiply certain numbers by -1. So there's a symmetry in the system. And we're discussing what are the ways that we can impose that symmetry onto our machine learning model so it knows that real underlying physical quantity. And one way of doing that is to have a term in the loss function that captures how much you violated physical laws, and you get a cost against that. So we've tried that methodology a little bit, and it has been useful for one or two problems.
Yeah. Okay, thank you. And another question. So I wanted to ask about any challenges you face with generalizability of the machine learning models. And can you say that a model that's trained with a wide data set can be used for like different battery families that are maybe more unknown?
I think that's a really good question, and it's very important how our models can be used as widely as possible. So if we are faced with an entirely new type of battery system that we've trained it on lithium-ion batteries, and we go and apply it to the lead-acid battery, so that's the type you'd find in your car, not electric vehicle car, your internal combustion motor car, then you'll find that it just won't work at all. That if it's never seen any data ever about lead-acid batteries, it's just not going to function. But what we can do is similar to the slide that I show here, that from the lithium-ion batteries, there are going to be some fundamental physical laws that the tool can pick up about batteries, such as the correlation between experiment and computer simulations. And then faced with this new kind of battery, you might well be able to get away with only performing computer simulations on this battery at all, and then use those, and then the tool will know that its internal correlation and be able to make a very good prediction of what the experimental quantity for that battery would be, even if we've never ever physically made one of those batteries. As that's the typical way that we would generalize out to dramatically new kind of battery.
Yeah, thanks. Also, a more general question. I was wondering what your opinion on would be for the remaining steps required, particularly like for electric vehicles.
So I think that there's lots of things we're going to need to get right for electric vehicles beyond getting the batteries right. So we still need the batteries to have a significantly longer range. Then we're going to need to get a much more widespread network of charging stations. And then here in the UK, lots of people live in what we call terraced houses. They park their cars on the street, and then they would need to run an electric cable across the street from their house. And we can't do that because then passers-by will trip up over it. And so we need to find ways of overcoming that, or they have to park halfway up the road. And then how can they charge their electric vehicle up at night? So there's that kind of a practical issue. Then we're also going to need the electric vehicles to be improved in many other ways. Can we make better tires that got less rolling resistance, that have a longer range? Can we perhaps, with the advent of self-driving cars, they might be able to drive much more smoothly than a human can to be more energy efficient? Can they set them up to tailgate each other on higher speed roads so that they have much less air resistance? Can we otherwise reduce the air resistance of these vehicles? And so there's a whole host of these practical issues that I think need to, or could also need to have wide scope for further improvement.
Thank you. Just checking. Oh, I have a question from the chat. They're asking, can you use partial differential equations to model battery usage?
Excellent question. So yes, we can. So that in that Nature Review article, there's a whole section about this kind of first principles computer simulation. So that might be an equivalent circuit model here, perhaps, that might have differential equations in it. And certainly, so we would then be embedding those in as a separate stream of data that, just as shown here, that would help augment our data stream. But it also raises another important question, which we have kind of been thinking about, is perhaps we can get the tool itself to learn about differential equations, that perhaps rather than doing property to property correlations, it might be gradient of one property is linked to a different property. So that is in effect a differential equation. And we have been thinking about doing that.
Thank you. And then I have another question here. So how do you use uncertainties in your work?
So of course the uncertainties are, okay, so there's two sources of uncertainty in the predictions. It could be that the experimental data originally has a lot of scatter on it, or it could be that we're extrapolating a long way, like shown the blue graph up on this page. So once we get the machine learning to make predictions of the uncertainty, then it's going to be very useful to help decide how to merge these data sets together, or merge these different quantities together to ultimately minimize the uncertainty in our final prediction. And then secondly, once we've got those uncertainties in our predictions, we are then using that when designing a material. That usually the customer will say, we would persuade them to say, I want a material this strong, this light, this cheap. And then we work out the composition that not only gives expected material properties that exceed those targets, so that's not using uncertainties there, but also we know what the uncertainty in our predictions are. And so we can actually work out effectively how many standard deviations we exceed those targets by, which you can translate into a likelihood that the material will actually work. And so what we're actually doing when designing a material to fulfill targets is maximizing that likelihood to find the material most likely to work given the data that we had available in the next experiment. And that's going to be much more effective than finding the material with the best expected properties, because usually what happens then is that you would extrapolate dramatically in composition space to some wacky material that's never been made, that if you just draw a straight line through the end of your results you have, it looks like it'll be a material with the most fantastic properties. But in actuality, you've extrapolated too far, and we would pick up on that through the vehicle of uncertainties, because it will have an enormous uncertainty on it. And so it's actually likely that in real life, it won't work. And so that usage of uncertainties is vital to actually make high quality predictions that actually work in real life.
Thank you. I have a couple more questions from the chat. So, how about temporary sparse battery monitoring data for remaining useful life? Do you have a specific approach for long and sparse time series to deal with such cases?
So I think for where the data sparse and the time series is very long, that we would opt to, we need to respect the time symmetry of the system, which would mean often, one methodology is a convolutional neural network, which respects invariance under time, or there's other mathematical transformations that we might opt to do instead, like take a Fourier transform with respect to time. This could be a good bet. Or we might translate the time series information into something that's a bit more capturing the exact physical quantities we want, which might be the charging cycle number, where the maximum charge fell below 90% of the original charge the battery could hold. Something like that, which would then remove that time x-axis on the time scale. Well, actually, one final thing that we can do, we haven't done it for batteries, but we have done it several times for other physical properties, is to handle data not just as a number, but as a little graph, so that this can come about with material properties as a function of temperature is often one, in which case actually our machine learning doesn't push a point around, but it pushes the graph around internally like a vector. And that then allows us to extract information about the graph.
That's very cool. I have more questions. So someone is asking, may I ask how you decided to overcome the sparsity in your data? Did you use traditional techniques or an adaptation to a neural network?
Oh, that's a very good question. So it was actually the second thing we did. We started out, it was just a chance project that I was doing with a Rolls-Royce sponsored PhD student. Well, I wasn't really involved, and we were chatting one night, and they were telling me about them designing materials and them not having good predictive methods. And I said, well, why don't you try machine learning, about which I knew nothing at the time. And then we went off and coded up, just downloaded some common Python library type machine learning tool, tried it out, and it proved to be effective for the data that they had at that time. And then we worked out all the probability or likelihood things and how important that was to stopping extrapolating. That was actually the first thing we got right. And then as we tried to apply the same methodology to other problems with Rolls-Royce, then we came across the sparse data. It was actually a project for designing a material for 3D printing, where at the time they had just 10 experimental data points about 3D printing, because it was a new process, new material that had not been explored before, but the input parameter space was 30-dimensional. And you can't get 30 parameters from 10. It's just mathematically impossible. And that's when we got my thinking cap on. And then realized that we asked them, what we asked the professor, what do you do? And they said, well, obviously, we know that material properties are correlated to each other. That in this case, we know that ability for 3D printing is very close to welding, because in 3D printing, you melt locally with a laser beam, and in welding, you melt locally with electricity. And if a material is good at welding, it would be good at 3D printing. And then I get my graph out and just look at it. And then I thought, well, can we replicate that in a machine learning model? And then a couple of master students later, we figured out how to do it in a very general and effective way. And that's how we kicked off.
Thank you. Another question from the chat. Were you measured? So did you measure of uncertainty confidence intervals or confidence regions?
Oh, that's a very good question. So the underlying tool actually prints out the full probability distribution. And this can be important because some materials might have a double peak probability distribution. So as a function of composition, it might bifurcate, and it might either have a phase transition or not, and get two properties, and so the probability distribution would go up, down, up, down. And sometimes it's important that we pick that up. So we do have that full knowledge, and we do use it on special projects, but the typical project that we're involved in, that I think we're just lucky we can make any vague estimate or any reasonable estimate of the uncertainty, and we probably shouldn't push our luck too much. And so in that case, we're working out where one standard deviation lies. That's within where, 2/3 of the point of the predictions fall. And that's a typical measure that we are using. So we're mapping it onto a normal distribution.
Yeah, thank you. I'm done all my questions and the questions in the chat so far. So I guess I'll wait another minute if anyone has any more questions. But other than that, thank you so much for the very interesting presentation. I think we all learned a lot, and thank you.
Thank you very much for inviting me. And it's absolutely fantastic that we can continue to work internationally, even when I can't leave the city centre.
Yeah, absolutely. Okay, I believe that's all the questions then. Thank you so much for everyone who attended the session as well. We host sessions like this maybe 3 or 4 times a week. So if you're interested, all of our information is on the ai.science website, and we have a lot of upcoming interesting sessions just like this one. So please go onto the website and take a look. Thank you, everyone. And thank you so much, Dr. Gareth Conduit, for joining us today.